This work is about the impact of the P3 microphysics on simulation of mesoscale convective systems in E3SM regional refined model. This was published in James last year, and Jiwen was the postdoc who was working with me on this. I would like to also acknowledge co-authors Jiwen and Kai Zhang, Eric Roslow, Ben Hillman, Kobe Shipand, Wu Yining, and Xiaochen Xie. I also would like to acknowledge the funding support from DOE CMDB and the E3SM programs. Next. Mesoscale convective systems play important roles in global hydrologic cycle, radiative budget, and circulation. But it's difficult to simulate in the global climate models, GCMs, because of coarse resolution. The regional refined model, such as at 1/4 degree, makes such kind of simulation possible. And cloud microphysics is one of the most poorly represented microphysics in GCMs. And it can affect MCS simulations a lot in the high resolution, such as CRM or CPM scale. The microphysical parameterizations in the released E3SM follows MG2. There are two significant limitations. One is the artificial conversion between from S to slow. As you can see from this schematic figure for how the S and the slow represented in MG2, there's a predefined artificial cutoff size. Another thing is the MG2 neglects the rammed particles that are very important hydromedias in the convective systems. And this would be very important if we're going to higher resolution to have these rammed particles considered. Next. The predicted particle properties, P3, these parameterizations developed by Morris and Meribot in 2015. This was the initial publication, and there's a few others follow-up on that for different developments. So this one can address both limitations. The ice particles are predicted or involved locally from small and dense ice to partially rammed ice to grub and hail, which is fully rammed. So that means we don't have this artificial conversion. Also, we have removed this predefined parameters and thresholds for the ice density, as particle density and the force speeds. The rammed particles are considered by predicting the rammed mass and the volume. So the scheme still only have 8 prognostic variables with the rammed mass and the volume replaced the slow mass and number in MG2. Next, please. So implementation of P3 to E3SM requires a few significant changes because P3 was originally developed for the high resolution at the CPM, CRM scale. So in order to make it work for E3SM, changes in the, we need to add the subgrid variability in the microphysical process rate, in add class action, and also scanning some tendency terms because the time integration here in the global model is much longer than the CPM scale. So here is a little bit of history about implementation P3 in E3SM. The initial implementation was on the CMDV MCS project, and this is started from version 0, then later version 1, mainly done by Kai Zhang. Later, Screen team refactored P3 and implemented this into E3SM for the 3-kilometer simulations. And then on the NGD project, we merged with the refactored P3 developed on the Screen, and then to have a single P3 code base. We then debugged and evaluated. This mainly done by Kobe Shiband. The code now is being used for the convective assessment tasks and also being evaluated for the version 3 release. But for this study, we still use the code developed on the CMDV MCS project. But the bugs we will find during the NGD debug processes, there's a couple of bugs applicable for our version, so we also applied. So physically, it should be very similar to the version we used in the NGD, but the code is refactored. It's different structure. There's a few features I want to mention about the code we used in this study. First, the heterogeneous articulation still follows the original P3, which is Big 1953 for immersion freezing and Cooper 1986 for deposition nucleation. This is different from the classical nucleation theory CNT used in our P3 under the NGD project. With CNT, the heterogeneous articulation can be connected with aerosol properties. So that is, we think it's a advantage. So we used the CNT in the NGD project. The homogeneous aerosol freezing for cirrus cloud still follows new and panel, which is the same as the previous version. Well, I want to emphasize that we corrected the aqueous chemistry bug, and this one originally, this is kind of a legendary bug for from the CESM. The total condensate mass was used for the aqueous chemistry. This was changed to liquid water content only, which is what it should be, and needed to smaller aerosol loading. Next. So here is a little bit of information about the simulation and also the analysis method. We used the Cornelius RRM 1/4 degree grid as shown here in the figure. So this is also from the code is mainly version 1, but we'll have some updates in version 2. We used large simulations with linear logging, only large wind. So we run the simulations for almost 2 years, but we are focused on the spring 2011 for the analysis. And there's a couple of observational data we regraded to 1/4 degree are used for model evaluation and for the MCS tracking. So the MCS tracking at 1/4 degree, this was developed under CMDV. This tracking scheme is applied to both observations and the model simulations. Next. So here is about precipitation and the PDF, the precipitation rates. So you can see from this red box, you see that over the large domain, this is almost the entire United States except the West Coast. So the mean value actually, P3 give less mean value closer to the observations than MG2. Then the major feature is the PDF. You can see the red line is for P3 and the blue is for MG2. You can see P3 has a particularly larger frequency. This is in log scale, so the change is actually pretty significant. So higher frequencies of larger run rates, larger than 30 millimeter per hour. Particularly, you can see we captured the run rates even larger than 45 millimeter per hour as observed. Next, please. So here shows from the large scale precipitation and the convective precipitation. As you can see on the top, the changes mainly comes from the large scale precipitations. On the mean, it's decreased, and the convective precipitation changes are small, and particularly on the run rate for those larger than 30 millimeter per hour, it mainly comes from large scale run rate. Next. So here showing the Hoffman figure. On the y-axis is the Dollar cycle, and then on the y-axis is the longitude. On the top is the total. You can see P3 predicted the next morning precipitation. On the top is morning. Lower part is the afternoon. Middle is the night. You can see we predict less morning precipitation, but more afternoon. Yeah, less morning and also less afternoon precipitation. But in the middle, the 12 a.m., you can see we predict more nighttime precipitation. This is, it's promising to go in right direction. But the magnitude is large enough to change the phase of Dollar cycle. So on the MCS precipitation, no, yeah. Can you go back a little bit? There's one point I want to make. Yeah, on the MCS precipitation, you can see clearly we have more MCS precipitation, which is the second row, and then non-MCS will have reduced. And regionally the changes are pretty significant on locally. Next, please. So on the MCS number, you can see overall the model have much larger, have much lower number, MCS number. This is a pretty significant problem, not just this model. It's probably pretty general. Still, the resolution is coarse. But P3 is be able to get 11 more compare MG2. And then while the model, both model underestimate MCS number so much. So from the bottom panels, you can see it's there's two thresholds we need to meet. One is the duration for convective system, the duration threshold. The other one is the dynamimeter, which is the size threshold. So majority of them, in the model, in both model, we have too much in the bottom quadrant. So you can see they cannot. Yeah, they meet the duration threshold, but cannot meet with the size threshold. So mainly because the simulated system are too small. And for this one season, P3 predicted 11 more, so it's significant. And why P3 predicted more? Next. Nguyen, I think you skip a slide. Oh, yeah, it is. Sorry, I deleted one. Okay, so yes, you can see P3 predicted higher precipitation rates. This is a time series. Generally, it's higher precipitation rate. And when we look at the differences, use some threshold to identify the periods that P3 has significant higher precipitation. Then we have this 26 time periods. And then here I also on the right, I show example of one of the case that MG2 missed, but P3 identified as a MCS. You can clearly see there's a high precipitation core that MG2 missed. Next. So as I just mentioned, we have this 26 time periods that MG2 has dramatically lower precipitation rates. So then what kind of synaptic systems dominate for those systems that MG2 missed, but P3 captured? So based on the SOM, we have these 4 major types of synaptic patterns. This is also identified from SOM 2019. And we find out when we look at the synaptic pattern before the convection initiation, and we actually find 21 of them, which is this type 1, type 3, they are from the frontal systems. This 15 from the third one, this also it's just a weak frontal system, that's the type 1. So only 5 from the GPLG associated systems. So this means that the P3 was be able to improve the large scale frontal system, I mean mesoscale. This is what we call a synaptic scale system that with larger, broader stratiform precipitation. That also makes sense, right? Because we change the stratiform, the large scale macrophysics. Next. So then why the P3 has larger precipitation rates? So showing here is for the macrophysics properties for those places with 10 with rain rates larger than 10 millimeter per hour. And on the top is mass, bottom is number. So first of all, you can see for the rain mass number, P3 has much higher rain mass and lower rain number. This already explains why we have a larger, those large, higher frequency of larger rain rates. And then when we look at it, this is mainly actually consistent with the ice, much more ice water content, and also less ice number. And you can see the auto conversion actually P3 has a lower value, so it's a lot from the warm rain. But the rammed ice, and sorry, I cannot use the pointer. So the rammed ice, which is on C in the red dashed. So there you can see compare the solid red solid. There's so the rammed ice only contributed 50 to 60% of the total ice mass. So there's a large increase also from the non-rammed ice, which is from deposition. So this shows besides added ramming, the deposition growth also contributed this increased ice mass. Next, please. So indeed, you can see we see the deposition. The deposition rates are several times larger in the P3. And this is probably also because the P3, 2 reasons. One is that in the polarization, P3, the deposition for P3 is treated for the total ice, while in the MG2, it's only treated for cloud ice. the slow is not included. The second is because we see this strong feedback. And the strong feedback also you can show from the condensation evaporation. You can see we have a large gain in total condensates. This is indicate stronger convergence. So when we look at the substance, indeed, P3 has a much stronger substance, and this indicates a stronger, larger instability, a stronger convergence. You can see also the relative humidity was changed. So that actually further will enhance deposition and condensation. Next. This is a summary. So I went through very quickly. I tried my best. So here the new Microphysics P3 improves the simulation of precipitation, particularly the PDF of the precipitation rates, by predicting more occurrences of higher precipitation rate. P3 improves the simulation MCS precipitation and the number, and this is because higher, we will predict more larger run rates. And this mainly comes from the increased ice mass and due to added ramming and also enhanced deposition. Of course, the force speed, the density force speed will be larger for the rammed particles. So here I want to mention that because the force speed and density are predicted, those we don't need to prescribe. This is the prescribed parameters were removed. So we show a loadable microphysical dynamic feedback here. So latent heat seems feedback to the dynamics and enhance convergence. So this missed MCS by MG2, but captured by P3 are mainly associated with large front systems with broad stratiform precipitation area. So I want to mention a little bit about the current work. So on the NGD, we are evaluating aerosol forcing, particularly the aerosol cloud interaction forcing for the latest E3SM with P3. So which is E3SM version 2 with P3 with the aqueous chemistry bug phase plus ZM with the microphysics. Thank you. I'd be happy to answer questions.